Okay, so let us pick up from where we left. We have this solution proposed by Badano et al. With this idea that we want to learn the similarity or score that how well a decoder state ST, aka the query, should attend to an encoder state HI, or the key value. This is done using a tiny neural network, an MLP, with one hidden layer and a tangent hyperbolic activation. So let us look closer at this formulation. We have WQ and WK as the length projections that map queries ST and keys HI into this common alignment space of dimension DH. So note that this let us compare ST and HI from different sizes. Let's say ST can be the decoder dimension and HI the encoder dimension, and not necessarily the same. So that's a nice feature. So again, this let us compare objects of different size. So you can imagine that this rotate and scale both ST and HI in a way that they are semantically matching. Then it will inject some nonlinear interaction using the tangent hyperbolic between the projected vectors that enables a richer non-bilinear matching. So beyond, let's say, a dot product or a cosine similarity. And then we have this VA that is basically a feature selector in this alignment space. So after computing the DH dimensional match features, now we have a vector of features with DH dimension following these steps here. But then later we also choose those features that actually matter in this alignment. So VA helps us to do that, to assign some positive and negative importance to each one of these hidden features produced by following the tangent hyperbolic. Okay, so note that this is defined for T and I, but we are going to share the parameters of this MLP for all pairs of T and I. Remember that this is very similar to CNN logic that we are using or learning a kernel, but we are using the same kernel across all pairs. Okay, so let's look at why this works. So first of all, it removes the bottleneck that we discussed. So this decoder no longer compresses this entire source into a single vector, and instead it adapts a context, dynamic context CT at each step. So now let us call this ETI, and then we can make this tension weights alpha T and I. That is basically a softmax of this. Like I said, this gives us the CT, and the decoder uses this CT and the ST to predict the next token. So again, we know what's nice about this soft alignment. These weights or the soft alignments behave like a differentiable alignment from this target position T to the source position I. So the paper from 2014 showed that using this additive attention significantly advanced the original seek-to-seek LSTM breakthrough by Ilya and others. So now let us look at how can we implement this. And before coding, I want to take a closer look on the scalability of this additive attention. We know that our GPUs and TPUs are optimized for this dense matrix multiplication. However, additive attention requires this kind of complex fused operation. It's not pure matrix multiplication. So if we could do the same thing, but only with pure matrix multiplication, we could achieve massive speedups and, of course, scalability, which is something that we need for training large models. So looking at this here, let's see what prevents us from this scaling up and going to our pure multiplication. So I'm going to rewrite this just for the sake of discussing this computation aspects. So let's assume this, we have T as the target length or the number of tokens, for example, in the French translation, and N to be the source length. Okay, so now we have WQ ST from T1 to T, which is in our TH, right? And on the other side, we have WKHI from I1 to N in this. The pairwise hidden feature will be, first, let's write the first component, H of, I'm going to make my notation easier by calling this guy a T from T1 to T, or short-handed by matrix A. And this guy, let's call it B from I1 to N, or B, right? So the tangent hyperbolic that we discussed will be AT plus B plus some bias term. And we know that this guy is in our DH, right? Let's call this H. Now, E, T, and I will be the feature selector multiplied by this H. Okay, so computing this naively requires OT and DH tensor, and of course an element-wise nonlinearity in 10H, and a reduction here. So this pattern is extremely broadcast heavy. It is memory bound, and it's not really using our GPU tensor core units. Like I said, what we really want is this generalized matrix multiplication. This way, if we do it, we can leverage all of this GPU cores, and we basically can achieve a hit peak or the maximum number of floating point operation. So note that this nonlinearity plus these two is not separable in our GPU. So I encourage you to look at this and see why it's not possible to separate and distribute it over our GPU cores. Okay, so let's move toward this kind of matrix multiplication version of this attention computation that we are going to call it an inner product or a dot product attention. Okay, so we want to do the same thing, but only with dot product. So how to do it? Basically, I like to do this calculation here, or this computation of attention of this guy here, in a way that I'm not dealing with any of these two. But we know that nonlinearity does something for us. It really enriches this latent space and finds better alignment. And also, this VA helps to add another level of feature selection. So we need to somehow build up this nonlinearity in our architecture in a way that we basically separate the building up of nonlinearity to achieve richer features. And then once we have that in this rich feature space, then we can do inner products without the need of infusing additional nonlinearity. Okay, so we'll explain what I mean by that. Okay, so let us state the problem that we want to solve. We want to find a similarity between two vectors, right? The query and the key. In our case, for example, Q was S of t and K was H of I, right? But we want to do it in a way that when we are computing this pair attention, we only want to use inner product, right? Between ST and HI, or some function of them, right? I mean, we can do any operation we want as long as it's on them separately, not under interaction. So let's call this functions phi, okay? So if we have this, then we can just compute the inner product. Let's use the classic inner product style notation. We want to find phi here, that in a way that the inner product gives us a kernel that is the most relevant kernel for our task. So we want to learn these phi's, and this will give us the similarity that we want, right? So where we saw this, if you remember in support vector machine, for example, we had this problem of separation of, let's say, a two group of data points like this with a linear plane or line. So this is a two-dimensional space, let's say. Let's call it x1 and x2. So in support vector machine, what we did was to find a higher dimensional space, let's say phi1 of x, phi2 of x, and phi3 of x, where things are separated. Let's say here you have this separation like this. So now with a simple plane between them, we can separate them. You can think of phi's, for example, here in this case, we have x was x1 and x2, but phi's are, I don't know, some form of functions of x1s and so on. Okay. So note that we can have any function here. For example, it can be sine of x1, cosine of x1, x2, anything. So, and how many of the functions we have in the world? We have infinite. And as long as we can compute the inner product, we are happy. And in this higher dimension space, things are easier to separate. We can employ linear operation to, for example, separate them, rotate them, and align them together. And that's the idea. So we need to build up a feature space using nonlinearity that we want, that on this ST and HI, and lift them from this lower dimension to this higher dimension, where things are easier to manipulate using our linear operations or linear algebra, and dot product is one of them. And as long as we are in this space, we can do dot product. So that's the real idea here. Okay, so let's go back to our seek-to-seek RNN, where we had type of RNN layer. We had several activation within the RNN that adds nonlinearity to the encoder and decoder states. And given that nonlinearity and some rotation of them, and the inner product of this will do what we want. But like I said, this is all relying on the case that we already have enough nonlinearity here, or we already lift this up to this higher dimension. So that's the idea. So we need the nonlinearity. We can not only do this rotation. Okay. Later you will see when we remove even the RNN or CNN encoders and we only do attention, we have to have some form of feed-forward neural network that injects this nonlinearity or lifting role. Okay, so remember when we go to self-attention, where we only have attention, we still need some form of feed-forward to infuse enough nonlinearity to lift everything up, and then in this higher dimensional space, we can do this inner product. We can also show this from the previous kernel view. So assume a Gaussian kernel, let's say a kernel between Q and K that is written like this, right? With some kernel weights, which is a function of this norm. So if we write this down, it is basically Q minus 2 QT K. So this is an inner product, right? So the idea is this is equivalent to this. So why? Because we know that later when we send this guy to softmax, softmax is invariant to shifts, meaning that, for example, if you have softmax of a q, let's say ki, plus some constant, this will be similar to softmax of a q ki. Okay, so anything that is constant here and not a function of ki that changes with I will vanish. Okay, so let's go back here. Well, this guy is a function of q, so it will vanish in a softmax. How about this guy? Well, we know that this is ki, right? So this shouldn't really vanish. But the thing is, in attention, we do this layer norm, which makes all of these features to be normalized, meaning that they all have the same norm. So all of the ki's has the same norm. So ki has the same norm as kj when I and j is not the same. This is happening because that's how we adjust them. This is the layer norm. So in that case, this is also a constant, and the whole thing reduces to the inner product. So we want to maximize similarity. We minimizing the kernel or the distance and maximizing the dot product because of this negative. Okay, so this is another way of looking at this. Okay, so it's important to know that after this calculation, we said that AQK basically same as QTK, but we also want to make sure that we are taking care of the variance here, because we can have a high dimension for these vectors, like we discussed. So the vectors, let's say they are living in decay, and the inner product basically is happening in decay. So even if Q and K, both the expectation is 0, they are centered, and even their variance is 1, we do this scaling, right? The variance of the dot product is the summation of all of these variances, right? Which is the dimension. And when dimension goes higher, this variance goes higher. So how to control this? We basically make sure that this guy is divided by dk. So we want to make sure the variance of this is not exploding with dk, and to do that, it's enough to divide it by square root of dk. So this is the notion of scaled dot product. And using this, now if you compute the variance will be 1. So that's the idea. We are going to use scale dot product of the WQ and WKK over square root of dk. So this is the scale dot product between the aligned vectors. So this is what we have so far, and we have the scale dot product that gives us this similarity. So of course we need to have a way to learn this Q and K using enough nonlinearity, and then learn WQ and WK to align them, and then this dot product that is scaled will give us the similarity that matters between Q and K. So this way we check those Ks that are the most similar to Q. Okay, so let's just move on to compute what we discussed that gives us the value of Q, right? So this is that. In the case of RNN, this is HI, but let's just stay general here. I'm going to simplify a little bit. I'm going to call this Q, this K, and rewrite this guy in a matrix form for all Qs and Ks and Vs. Okay, so remember that we want to compute the kernel regression. If you remember, we learned the kernel, but we have to do a softmax over that kernel, and then multiply by vi. This gives us this pooling, and if we write this with this, it's basically softmax of q kt scaled multiplied by v, and this is called attention, which is a function of q, k, and v. We learned k and q with enough nonlinearity. Then wq and wk that align them, and then pass it to softmax, multiply by the values, and that's the attention pooling. Okay, next, we are going to code up dot product attention and show the simplicity of this idea. But of course, we have to remember where it comes from and why we can do it, because of all of these nonlinearities that lift our data to a higher dimension where the linear operation and linear alignment is possible and rich enough that gives us enough learning from data to do the task, for example, translation or token generation.